Hey everybody, I got a request for some more information on this Module 6 problem for the combined Otto and Brayton cycle. So I put together some notes, wanted to do a quick video on it to give you something to help you get started. Some of these things may not be obvious. So this problem it's a custom hybrid process. It's not a standard power cycle because we're doing a Brayton cycle in compression, and then a full Otto cycle, all 4 points on an Otto cycle, and then a Brayton exhaust cycle. So the point of this is you've done Otto cycles, and we've learned Brayton cycles, so now we're just adding the Otto into the Brayton cycle. So the Brayton cycle compressor creates the boosted intake condition. So that boosted condition becomes the starting point for the Otto cycle. From there, the Otto cycle follows its normal compression, heat addition, expansion steps. The most important thing to understand is that you're not solving the whole thing with one equation. You're just solving it process by process and point by point. So let's give me some space to write here. And so for each state, so you need a table. You need a way to organize all this stuff. And the way we're going to do that is a table. And on this table, you should have, I don't have that screen up. Temperature, pressure, then you have to have enthalpy, internal energy. So I'm just going to shorthand that, H, U, and then your relative pressure and your relative volume, P, R, P, V, and then, of course, Q. That doesn't follow up fit on the screen, does it? On the bottom is Q. Now, what I would do is, like I give you in the example, the setup for the problem is just set up a table, set up columns, and these column titles would be, I think I used like state 1, state 2, state 3. Maybe it's better to label it Brayton point 1, Brayton point 2, Otto cycle 1, Otto cycle 2. So I might do B1, so that's the input to the Brayton cycle, and I would have my table there. And then B2, this is the output of the Brayton cycle, but it's also O1, Otto cycle 1, Otto cycle point 2, Otto cycle point 3, right? And then 4, Otto cycle point 4 is B3. And that's going to write over my face. But you get the point there, right? So now you got your table, and it's just filling in points. So it's finding the points on the air tables. And there's just, I think maybe the hardest part of this is understanding how you're getting input for B2, because B1, I give you temperature is 17 or 70 degrees Fahrenheit, and I gave you 14.7. I don't have room for the units, SIA. And so you can go to your air tables. Let me find my air tables and fill in those points. I'll give you this data. The air tables start on page 89 of your student text. So internal energy, I got enthalpy. Enthalpy, H, for 70 degrees Fahrenheit is 126.41. I don't have room for units, so I'm just going to leave those off, but that's BTUs per pound mass. And then next to that is internal energy, 90.7. And then you can also look up that, and there's nothing for Q because we're not adding any heat at this point. So now, Brayton 2, it goes through a compression, but what information do I give you about compression? I give you turbo boost, and what screen do I have the problem on here? I give you turbo boost. Give me one sec. I give you a turbo boost of 3 psi. So 3 psi, create some space down here. 14.7 is where we're starting, plus 3 psi of boost gives me 17.7 psi. And so this becomes my pressure for starting point 2. Well, then I go to, now I can calculate the pressure ratio, right? Now I have a pressure for B1. I have a pressure for B1, and I have a pressure for B2. I have an initial pressure ratio. Now I can calculate the second pressure ratio. So my pressure ratio is, it's a clean way to do this without erasing everything. Erase this. Okay, now that I've got my pressure at B2 and my pressure at B1, I can use the Brayton relation to find pressure ratio B2. So I've already divided, went ahead and wrote in the pressure ratio at 1, and I divided out pressure at 2 over pressure at 1, which is 17.7 divided by 14.7. And that gave me 1.204. So pressure B2, let's write out the equation, pressure ratio of Brayton 2 equals, and its pressure ratio of B1, which is 1.28, can't read my own writing, 3, times that 1.204, which is, and 1.204 is pressure of B2 over pressure of B1. So this is 1.204 times pressure of B1, 1.283 equals times 1.283. It gives me a pressure ratio 2 of 1.544. So now that's how I find my B2 points. So I go back to my air tables and I look for a pressure ratio. So I'm looking in the pressure ratio column and I'm looking for 1.544, and I'm just going to use the closest one. And it tells me it's 100 degrees Fahrenheit. So 100 degrees Fahrenheit. And I already know the pressure, and then I can look at the enthalpy for that 100 degrees, and I fill in the enthalpy, I fill in so I just fill in all these things after calculating pressure ratio 2. Once, yeah, so you find all those points, and we're not adding any heat yet, so Q again is just a big X. That is now the input to the Otto cycle. So we go back to the Otto cycle. So B2 is state 01. That means the entire Brayton compressor outlet condition becomes the Otto inlet condition. So this is a good, yeah, I'm not going to make it confusing about the turbo and blah, blah, blah. Doesn't matter. You go back in your student text, because we were on the Brayton cycle little chart. Now we go to the Otto cycle. The Ottos, let's find the page for the Brayton cycle was page 57. The Otto cycle's page 48. And I'm doing this just by reading these steps. Like the only thing I had to know is I'm adding 3 psi of boost in the compression cycle. And so I know how high I'm raising the pressure. And so I just add that 3 psi to the inlet pressure. I get my outlet pressure, and then I figure out my new pressure ratio using that Brayton table on page 57. And so now I'm back to the Otto cycle on page 48. And so I have my initial U1, I have my initial VR1. So my R is V1 over V2. And then using that Otto cycle relation, VR for step O2, Otto cycle 2, is VR of O1, which is B2, divided by R. And R is just my change in volume. Well, I gave you that. I gave you the change in volume. The compression ratio is that change in volume, 8.8 to 1. So 8.8 to 1, yeah, is my R. R times the VR of O1. Yeah, you just keep going through all these steps. You're looking up these points in the air tables. You're just applying that turbo compression, and then you're applying the compression ratio to the Otto side. So that compression, the turbo boost, applies to the Brayton cycle. The compression ratio applies to the Otto cycle. All right, I hope this helped. I hope this gets you started, and yeah.